Okay, for problem D 7.129, it's given that the average value of the input signal, so this signal here, is 0 volts, and beta, so for the common base, the current gain beta for this NPN transistor is 100. And in part A, we need to find RE for a emitter current of 0.5 milliamps. Okay, so for part A, we know that we have a current IE here of 0.5 milliamps, and we basically need to define what's the value of RE for that to be true. Okay, so we need to determine this VE here first. Okay, and our first assumption is that the transistor is operating in the active mode region, so we know that VBE is equals to 0.7 volts. So this one here is 0.7. And again, because this analysis here in part A and B, it comes from the DC analysis, we know that the average of the input signal is 0. So it means that VB here at this node, the DC value is equals to 0 volts. So we know that. And assuming active mode operation, we have VBE equals to 0.7. So if we expand this VBE, here is VBE minus VE, is equals to 0.7. Now this one here we know that's 0. So this gives us VE equals to minus 0.7 volts. Okay, now that we know VE here, and we know the potential here, minus 3 volts, we can calculate RE so that we have that 0.5 milliamperes. So VE minus those minus 3 volts should be equals to IE times RE. If we isolate RE, we get VE, which is minus 0.7, so 3 volts minus 0.7 divided by the emitter current, which is 0.5 milliamps, and this gives us an emitter resistance of 4.6 kilo ohms. So that's the first, this is part A. Now for part B, so let me put this part B here, up here. Now for part B, we need to find RC so that we have a collector voltage of 0.5 volts. Okay, so one thing is that because we know beta and we know IE, we can calculate the collector current. Okay, so the collector current is equals to alpha times IE, and that's the same as 100 divided by 101 times 0.5 milliamps. So the collector current that we want for the NPN operates in the active mode region is equals to 0.495 milliamperes. So that's the collector current. Now because we know the collector current flowing here, and we want to have this potential here as 0.5 volts, we can again use the same rule that we applied here for VE, right? But now calculating RC. So one thing is that we know that 3 volts minus VC should be equals to RC times IC. So RC is equals to 3 minus VC, so VC is 0.5, divided by the collector current, that is 0.495 milliamperes. So this thing here is volts, and this gives us a collector resistance of 5050 ohms. Okay, so this is RC. Now for part C, let me go down here. For part C, we need to consider a load resistance. So this load, now we are going to analyze the circuit in do the small signal analysis. So now those capacitors here, they become a short circuit. Those voltage sources, they are all grounded. Okay, and we now have the small signal connected to the base. So we need to consider RL, so the load resistance as 10K, and draw the small signal model and determine the overall voltage gain, V out over V signal. So one thing is that we can use the hybrid pi model, and for that we need to calculate the transconductance, so the transconductance GM. Okay, and we know that the transconductance GM is equals to IC over the threshold, the thermal voltage, sorry. So it's 0.495 milliamps divided by 25 millivolts. This gives us a GM of 0.0198 volt per volt. And we also need to define R pi. So R pi here is equals to beta divided by GM, and that's the same as 100 divided by 0.0198. So R pi is equals to 5050 ohms. Okay. Now, if we plug in, so if we short circuit the DC voltage sources and substitute the NPN transistor here by its hybrid pi model, considering these parameters here and here, we get this circuit here. Okay, so if we go back to the circuit here, RE again is grounded, right? So this one here is taken out of the circuit, so it goes directly to the ground. The emitter here goes to the ground. Okay, so that's what's happening. So we have the base here, we have the collector here, and here we would have a connected going to the emitter, but remember that the emitter is grounded, so that's why we have this ground here and this ground there. But it's basically the same thing, right? We could like connect this entire thing here and say that everything is grounded, right? The way the circuit behaves, that's true. And that's the circuit that we have, the small signal circuit. So one thing now is, how do we define the overall voltage gain? So we need to obtain this equation here, okay? And first we can define V pi over V signal. So if we look at this branch here, we can apply a loop analysis here to determine this V pi, right? So V pi is equals to V signal. It's basically applying a voltage divider, right? The voltage across R pi is the same as V signal times R pi divided by R signal plus R pi. And that's the same V signal. So if we isolate V pi over V signal, that's the same as R pi. So R pi is 5050. 50/50, so 5k ohm, roughly 5k ohm, divided by 5k ohm plus the signal resistance. And the signal resistance is 2.5, so this one here is 2.5k. So plus 2.5k. And this gives us a V pi over V signal that is equals to 0.6688 volt per volt. Okay, now the second part is determine the ratio between V out and V pi. And again, if we look at this circuit here, V out is the voltage across this parallel here, right? It's actually this voltage, V out, is this current GM minus this current GM, because it's going in the opposite direction of the polarity of V out, times the parallel between RC and RL. So we can basically calculate V out equals to minus GM V pi times the parallel between RC and RL. And that gives us V out over V pi that equals to minus GM times RC times RL divided by RC plus RL. So V naught over V pi is equals to minus GM, so 0.0198 times RC. So our RC we define it as 5K times RL, so RL it's given 10K divided by 5K plus, so that's almost that, times plus 10K, and this gives us minus 66.43 volt per volt. And again, if we look at this part here and this part here, if we multiply both quantities, we get, so let me go down here, we get V pi over V signal, right, times V out over V pi, and that's equals to the overall voltage gain. That's the same as 0.6688 times those minus 66.43. So at the end, V out over V signal is equals to minus 44.43 volt per volt.